Hello everybody, welcome to our lectures in MA3343 groups for week 3. So we have two main concepts this week to talk about. The first one is subgroups and the second one is generating sets, and they're quite closely related. So this short video will be the first of the two on the topic of subgroups. So before getting into the formalities, I guess something that algebraists generally like to do when they're studying algebraic structures is to figure out if the objects that they're interested in have contained within them some smaller things that also share some of the same fundamental properties. So at this stage, we know what a group is. It's an algebraic structure that satisfies some specified properties. And basically within that, you might have a smaller one that also satisfies the same rules, satisfies the same criteria, and that's a subgroup. So formally, the definition says, suppose we have a group G with an operation, which we'll just call star, and we've got a subset of G, then that subset of GH is a subgroup if H itself is a group under the same operation as G, so the operation star. Okay, so the definition kind of makes sense. It's presented in a very abstract context, and this is something that we have to get used to, the idea that, you know, a lot of the time in group theory, you're basically engaging in some sort of reasoning within some group, and it's just some completely abstract group with an operation that might have a name, and you know nothing more about it except that the operation satisfies the group axioms, associativity, the existence of an identity element, and the fact that every element has an inverse. And with just that, you're trying to sort of reason about what sort of objects might live inside the group, what sort of properties they might have, what kind of structures you might have within it. That's what we're doing here. And you know, if you find it kind of difficult to be moving between, to be kind of in this very abstract context where you don't really know what the things are that you're talking about, they're just some objects that satisfy the group axioms, then a useful exercise, I think, is to have some examples in mind. And, you know, whatever the abstract theory is that you're developing, keep thinking about how it applies to your example and try to practice moving between the abstract theory and the example. So with that in mind, here are a few examples of this phenomenon. So the first assertion is the set of even integers, which I'll write as 2z, is a subgroup of the set of all integers, the group of all integers under addition. So the assertion there is that the set of even integers is itself a group under addition, and it lives inside the bigger group consisting of all integers under addition. Okay, so do we believe that? Well, to answer it, we have to ask ourselves, the set of even integers, is it closed under addition? If we take a pair of even integers and add them together, do we get an even integer? Okay, the answer is yes, we do. If you add two even integers, the result of that will always be even. Okay, second question, does the set of even integers have an identity element for addition? Okay, there we say, yeah, the integer 0 is even. It's within the set 2z of even integers, and it's an identity element for addition. So yeah, it does. Then the third question, does every even integer have an inverse element for addition that is also an even integer? Okay, so even integers are things like 2, 4, 6. Their inverses for addition are -2, -4, -6 are also all even. So it is certainly true that the additive inverse, which is the negative of an even integer, is itself even. The additive inverse of -8 is 8. The additive inverse of 12 is -12. So yeah, so it is true that the set of even integers within the set of all integers is itself a group under addition. Try to do the same thing with the set of odd integers as your starting point, and you'll find that it's not a group for various reasons. So that's one example, a subgroup of the additive group of integers. Second example, if we look at the group S4 of all permutations of the set 1, 2, 3, 4, so all functions from that set to itself that send everything to a different image, that rearrange the 4 elements 1, 2, 3, 4. Within that, we could look at the subset consisting of all those elements that map 4 to itself. Okay, so if a permutation maps 4 to itself, then it shuffles 1, 2, 3 amongst themselves. So basically, the set of all permutations that send 4 to itself within S4 can be regarded just as the set of all permutations of the set 1, 2, 3 living inside S4. So in technical terms, what you would need to do to confirm this would be say to yourself, okay, well, if I take two permutations that are in this subset, they both map 4 to itself. If I compose them, does the result of that map 4 to itself? Does the identity permutation have this property of sending 4 to itself? Yes, it does. If I take a permutation that sends 4 to itself, does its inverse also set 4 to itself? The answer is yes, because the inverse of any mapping, any permutation that sends 4 to itself must send 4 back to where it came from. So it must also fix the element 4. So, you know, if you're thinking about this and what I've just said is kind of is too fast and too much in one mouthful, then something that you can do is, you know, write down the elements of S4 that send 4 to itself. There are only 6 of them. It's not such a long list. And just look at what happens to them when you compose, when you look at their inverses. Note that amongst those things is the identity element, and you'll see that yes, within S4, we have this sort of copy of S3. The subset of S4 consisting of those elements that fix 4 is exactly a copy of the group of all permutations of S3 that lives inside S4. And of course, there's nothing special about 3 and 4. This is true in general. We have copies of SK living inside Sn if K is less than N. Okay, third example. In the dihedral group D2N, so we've talked about D6 quite a lot, the group of symmetries of the regular equilateral triangle. In general, D2N is the group of symmetries of the regular polygon with n sides. So D8 is the group of symmetries of the square, for instance. D10 is the group of symmetries of the regular pentagon. D2N has n rotational symmetries. Okay, it has a rotational symmetry that goes through an angle of 2 pi over n, and then all the multiples of that. And it has n reflections. And the reflections, in the case where n is odd, are in the axes that pass through a vertex at the midpoint of the opposite side, as in the triangle. In the case where n is even, the axes of reflection either pass through 2 opposite vertices or through the midpoints of a pair of opposite sides. And within there, we'll find that the set of rotational symmetries is a subgroup. And again, you know, I kind of encourage you to have a look at that. Think about why it is that if you compose 2 rotations, you get a rotation, if you're talking about symmetries of a regular polygon. The inverse of a rotation would be a rotation, and the identity element is a rotation. It's the rotation through 0 degrees. If you try to look at the set of reflections and ask yourself, is that a subgroup? You will find that it's not. A nice exercise is to sort of think about that and explain why it's not. Because that's the concept of a subgroup. It's basically a smaller group that lives inside a bigger one with the same operation. I should mention that every group has itself as a subgroup. And every group also has a subgroup which consists only of the identity element. Again, that subgroup is called the trivial subgroup. So most groups have other groups that are intermediate, that contain more than just the identity element, but less than the entire group. And those are generally called proper subgroups. Okay, so generally, you know, something that we often have reason to do is consider the question of whether a given subset of some group that we know about is a subgroup. And if we are asked to do such a thing, there are essentially a couple of things that we have to consider. So here's an example. If we look at the set of non-zero complex numbers under multiplication, which we have been denoting by this C with a multiplication symbol. So this is non-zero complex numbers with multiplication as the group operation. And of course, you have to know what the group operation is before you can do anything. So make sure that you sort of make an explicit note of reminding yourself of what that is before you launch into an exercise like this. Okay, inside that, we're asked to consider the set of complex numbers whose modulus is a non-zero rational number. So remember what the modulus of a complex number is. It's basically the distance of that complex number from the origin in the complex plane. So if your complex number is a plus bi, its modulus is the square root of a squared plus b squared. It's the distance from the origin to the point ab in the real plane. Okay, so it's the square root of a squared plus b squared. The question is H a subgroup of the entire group of complex numbers under multiplication? Okay, so there are 3 things to check. And something that I should mention, which I didn't mention on the last slide, is that we don't need to check in this context whether the operation is associative. And the reason for that is because we know that we're talking about a subset of something which is a group. Okay, so the operation of multiplication is associative on the set of all complex numbers. So there's no way that it could fail to be associative on some subset. It is an associative operation. So generally, when you know that something is a group and you're asked if some particular subset is a subgroup of that, you don't have to worry about the associativity part. It kind of comes for free from the fact that the bigger thing is a group. We do have to ask ourselves, is H closed under multiplication? And this is kind of a fundamental thing, and it definitely has to be checked. So what we're asking there is, if we take 2 complex numbers that are elements of H, and we multiply them in the complex numbers, is the result of that still going to be an element of H? This always has to be checked if you're going to consider whether something might be a subgroup of a bigger group. And you know, the details of what's involved in checking it, of course, depend on the operation in question, but the sort of format is always the same. To ask ourselves whether H is closed under multiplication, what we have to do is give ourselves two elements of H. And we have to look at their product, the complex numbers. So X and Y are elements of H. What does that mean? It means that X and Y are complex numbers. Both of them have the property that their moduli are rational numbers. So this is telling us that the modulus of X, which remember we denote by X with bars around it, and the modulus of Y is a rational number. Okay, and again, that's not, that's not something that's true for every complex number. It's entirely possible for the modulus of a complex number to be an irrational number, an irrational positive real number. So that's fine. X and Y are elements of Q. They're rational numbers. Okay, remember what it means to say that they're elements of Q is that they are rational numbers. They're also non-zero rational numbers because the complex number 0 is not an H. Okay, it's H is a subset of the group of all non-zero complex numbers. Okay, so we have to ask ourselves, is it true that the product xy belongs to H? What does that mean? Well, the product xy we know is a non-zero complex number. So to ask whether it belongs to H, what we're asking is whether its modulus is a rational number. What we know about X and Y is that their moduli are rational numbers. So what we can say as well, and here we have to use something about our knowledge of complex numbers as well, the modulus of the product of two complex numbers is the product of their moduli. Okay, and since X and Y are rational numbers, their product is also rational. So we're making use of a lot of machinery here that sort of turns up again and again. The fact that the modulus of the product of two complex numbers is the product of their moduli. The fact that the rational numbers are closed under multiplication. If we take the product of two rational numbers, then it's also rational. So the conclusion then is that yes, the product xy belongs to H whenever X and Y are elements of H, and we can make an affirmative answer to the first question. Yes, this thing is closed under multiplication. So it is itself an algebraic structure, and it has some possibility of being a group. Okay, so that's what we have to do. Whenever you want to decide if some subset of a group is closed under the group operation, this is what you have to do. Give yourself two elements of the subset. If membership of the subset is defined by some property, like having rational modulus, then you know what it means for these two things to be elements of the subset. Combine the two things under the group operation. You have to look at what happens to this property, this criterion for membership of the subset, when you combine the two elements. If it survives, then your subset would be closed under multiplication. In this example, the criterion for membership of the subset is having a rational modulus. That is something that survives under multiplication of complex numbers, in the sense that if you take two complex numbers that have that property and multiply them, the product has that property as well. Okay, so that's part of what we have to do. Second thing, does H contain the identity element of the multiplicative group of complex numbers? Okay, so the identity element in the multiplicative group of complex numbers, of non-zero complex numbers, is 1, which if you want to write it as a complex number, the usual form is 1 plus 0 times I. Its real part is 1, its imaginary part is 0. Okay, its modulus is its distance from the origin as a point in the complex plane, which is 1, which is certainly a rational number. So yes, the identity element of this group does belong to the subset H. And that's another affirmative response there. That's good. And then the third thing is, does H contain the inverse of each of its elements? Well, if X belongs to H, then the modulus of X is a rational number, and it's not a zero. It's not zero because the zero it does not belong to the group of non-zero complex numbers. What we have to ask ourselves is the element X inverse, does its modulus also, this modulus also rational, and x inverse here means 1 over x. This is the modulus of the complex number 1 over x, which is just 1 over the modulus of x. So the conclusion is yes, x inverse also is rational. And that means that x inverse passes the test for membership of H. Okay, so again, it's a positive answer there, and the conclusion is, from all three of these observations, that H is a group, and it's a subgroup of the group of complex numbers under multiplication. Okay, so this is kind of a very typical example of deciding whether something is a subgroup. I mean, there's all these things we need to do essentially, and again, we don't have to worry about the associativity because it holds at the higher level, so it also holds within the subset. So there's a few more. We'll meet a few more examples like this as we proceed, and it's a good skill to have to just kind of both fully recognize what has to be done to show that something is a subgroup, and also practice examples of doing it in different cases. Okay, there's one important class of subgroups, which is the last topic for now, and that is the class of so-called cyclic subgroups. So this is something that's really, well, yeah, it's a very important concept that arises again and again in group theory. And I suppose, group theorists like to know, I have some group, I want to study it. What kind of subgroups does it have? That's a sort of basic question. Sometimes there are some kind of that spring out at you that are easy to see, sometimes not. But you might ask, well, how, okay, I've got this big group. I don't know much really about it. I want to know some details about it. How can I construct subgroups? And there is one way of constructing subgroups that always works. And that's by taking an element and looking at the subgroup that you can get from that element. And let me explain what I mean by that. So supposing we have a group G with an operation star. Okay, so that means it satisfies the axioms. That's all we know. And we give ourselves an element of G. So A here is an element of the group G. Okay, and we can ask ourselves, well, suppose we had some subgroup of G that contained the element A. What else would it have to contain? Okay, so we know what it means for something to be a subgroup of G. It means that that thing is itself closed under the operation of G, that it contains the identity element and it contains the inverse of each of its elements. So if you have a subgroup that contains the element A, and you don't know anything about the element A, except that it lives in a group, but any subgroup that contains A would have to be closed under the operation star. So it would have to also contain the thing that you would get by composing A with itself. And it would have to contain the thing that you would get by composing the result of that with A, because it would have to be closed under the operation within a subgroup that contains A. So you can sort of think about this and start writing down things that would have to be in this subgroup. So within the group G, we can combine A with itself under star to get A star A, which is probably a different element from A, in nearly all cases. And you can repeat this process and build this sort of sequence of elements of A. Here's A itself, and here's A star A. And the key point here to think about is any subgroup of G that contains the element A would have to also contain A star A, because of the fact that it would have to be closed under the operation star. It would have to also contain, now it contains A star A, it would have to contain A star A star A, which arguably I should write with parentheses like that, but because we know we're in an associative situation, we don't have to bother with that if we don't want to. And it would have to contain the result of composing that thing with A, and so on. So we get this list of elements that would have to be included in any subgroup of G that contains the element A. Let me just mention that it is a very usual shorthand in group theory, if you're in an abstract context like this, to write the first element there is A star A. There is a habit that group theorists have of writing that as A squared, and writing the next one as A cubed, and this one is A to the fourth, and so on. And just interpreting A to the fourth to mean A star A star A star A, whatever the operation is. And maybe we don't even know what it is, but to use that kind of shorthand notation instead of writing all the stars. That's a convenient shortcut when you get into the habit of using it. It doesn't mean that we're assuming the operation is multiplication or anything like that. It's just a way of keeping track of. So A to the fourth just means A composed with itself 4 times like that. Okay, so any subgroup of A any subgroup of G, sorry for that typo, that contains A must be closed under the star operation, so it must contain all of those elements in that list, which might not necessarily be all distinct. So for example, it's entirely possible that the element that you get by composing A with itself 6 times could be the same as the element you get by composing A with itself twice, and we'll see examples like that. But certainly any subgroup of G that contains A must contain all the things in that list. it must also contain the identity element, and it must also contain the inverse of A, and it must also contain all the things that you can get by composing the inverse of A with itself as many times as you want to do it. Okay, so basically, by starting with a particular element A, you can look at all the powers of A in the group, just like we did for the positive power. It's kind of a shorthand notation to interpret this thing and write it as A to the power minus 2. People do that all the time. And that just means, if you see that in a group, it means the inverse of A composed with itself. And A to the power minus 3 would mean the inverse of A star inverse A star inverse A. So then you can sort of write them all as powers of A, which is reminiscent of the list of all integer powers of some integer or something like that. And it's interpreted within this group context. So any group that contains A must contain all these things because of the fact that it has to be closed under star, it has to include the inverse of A, and it has to include the identity element. And the other side of that is that the set of all those powers of A do form a group. The details of the proof of that are in the lecture notes, and I'll advise you to have a look at them there. But basically, you can show that this list is closed under star. It contains the identity element, obviously. It contains the inverse of each of its elements. So it is a subgroup. It's called the cyclic subgroup of G generated by the element A, and it's denoted by this notation, A with these kind of angle brackets around it. So if you ever see that in group theory, you have to kind of remind yourself of what it means. It means the subgroup consisting of all the positive powers of A, the things you can get by composing A repeatedly with itself, the identity element, the inverse of A, and all the things you can get by composing it with itself, and it's always a subgroup. So basically, this concept of a cyclic subgroup gives us a mechanism, given any element of a group, to produce a subgroup that contains that element, and that in fact is the smallest subgroup of the whole group that contains that element. It might itself be the whole group, that's a possibility, but typically it's not, and frequently it isn't. If it is, that's kind of an interesting case that we'll talk about in the next installment. Okay, so that's the idea of a cyclic subgroup. So that's a lot of bombardment. It's abstraction again. Let me have a look at a few examples. Here are just two examples, but they're two examples that do different things, and both, I think, give a reasonable sort of description of what a cyclic subgroup can look like. Kind of different in both cases. So if you look in the set of integers under addition, so take an element of that, and 5 is a very nice element, so let's take 5. And okay, given any element, you can talk about the cyclic subgroup that it generates. So the cyclic subgroup of the integers generated by 5 has to contain 5. It has to contain the thing you get by composing 5 with itself. It has to contain the thing you get by composing 5 with itself again, 3 times, 4 times, and so on. It has to contain the identity element. And again, to remind yourself, what is that? Well, we're talking about addition in the integers. The identity element for that is 0. It has to contain the inverse of 5. It has to contain the thing you get by composing the inverse of 5 with itself under the addition operation. It has to contain the thing you get by composing the inverse of 5 with itself again, and so on and so on. Okay, so it's this infinite list. And of course, we can do the addition in all these steps. We don't have to write them like a list of 5. So we get 0, 5, 10, 15, and so on. We get minus 5. We get minus 10. Okay, that's the cyclic subgroup of integers under addition generated by 5. And of course, we can see that as we continue this list in both directions, we just get more and more multiples of 5. So this is the group of all integer multiples of 5 under addition, and we can confirm that it's a group. Sure enough, if you add 2 things that are there, you get add 2 multiples of 5, you get a multiple of 5 as the result. The 0 element is there, that's the identity element, and for everything that's there, its inverse is also there, since if x is a multiple of 5, then minus x also is. So this is the additive group consisting of all integer multiples of 5. And it's the cyclic subgroup of Z generated by the number 5. And just a remark, if you started with minus 5 instead of 5, you can observe that you get the exact same cyclic subgroup. So it's not necessarily true that the cyclic subgroups generated by all different elements are different subgroups. They can coincide. Okay, and the second example, which is maybe an interesting one because it doesn't, it's slightly unpredictable. In GL2Q, that's the set of 2 by 2 matrices of non-zero determinant over the rational numbers under matrix multiplication. And here's an element. Let's give it a name. Let's call it A. So we want to talk about the cyclic subgroup of GL2Q generated by that element. Now, this looks like it's going to be a huge thing, because if you start with A, you can start multiplying A by itself, you get another 2 by 2 matrix, you can multiply by A again, you get another one, and so on. So it looks like it's going to be an infinite list, like in the first example, only with more calculation to do at each step. But let's see what actually happens when we look at some powers of A. So we've got A itself. A squared is the matrix A multiplied by itself. And of course, we can calculate that. It's just a 2 by 2, so we can do that. At the top left, we get 0 minus 1. At the top right, we get 0 plus 1. The lower left, we get 0 minus 1. And in the lower right, we get minus 1 plus 1, so we get 0. Okay, that's A squared, that's fine. That should be in our cyclic subgroup generated by A, of course. If we look at A cubed, we get A squared, which is minus 1, 1, minus 1, 0. Again, multiplied by A, which is 0 minus 1, 1 minus 1. And we do that calculation. We get 0 plus 1 in the top left. That's 1. We get 1 minus 1 at the top right, that's 0. The lower left, we get 0 plus 0. And at the lower right, we get 1 plus 0. So we already get the 2 by 2 identity matrix after taking the cube of A, which is quite an interesting thing. And of course, if we can observe that because the cube of A, so this example wasn't chosen randomly, it was chosen for this very reason. A cubed is the identity element already of GL2Q. So that means if we take A to the 4th, it's just A again, it's the identity times A. If we take A to the 5th, it's A squared. If we take A to the 6th, it's the same as A cubed, which is the identity element. So we can note, for example, A to the 4th is equal to A, since A cubed is the identity. A to the 5th is equal to A squared, and so on. So, you know, by taking more positive integer powers of A, all we do is just cycle through A squared, and the identity element. A to the 6th is the identity element again. Okay, and also, the inverse of A is just A squared. So by taking the inverse of A and throwing it into our group, we don't get anything that we don't already have. We already have that as a positive power of A. The identity element is equal to A cubed. So all the positive and negative powers of A are just repeats of the first 3 positive powers. The inverse of A is A squared. The inverse of A composed with itself, multiplied by itself, is A to the 4th, which is equal to A. And the whole list is just, it just consists of these 3 matrices, the identity element, A itself, and A squared. So what we can observe is the cyclic subgroup of GL2Q generated by that particular element A just consists of A squared, and A cubed, if you want to write it this way. The identity element, we put that one first because it's kind of conventional to write the identity element first. That's 0, 1, 0, 0, 1, which also happens to be equal to A cubed. A itself is 0 minus 1, 1 minus 1. And A squared is minus 1, 1 in the first row, minus 1, 0 in the second. And those are the only 3 matrices that appear in this. This is A squared. So I'm not saying that the other powers of A and the inverse of A aren't here. I'm saying that as it goes through all of those powers in the list, A squared, A cubed, A to the 4th, A to the 5th, A inverse squared, and so on, all you get are repeats of these 3 elements. You can check easily that the set consisting of these 3 elements is closed under matrix multiplication. A and A squared are inverses of each other. A cubed is the identity element, so it contains an inverse for each of its elements. It contains the identity. It's associative because matrix multiplication is associative. So it's just a subgroup with 3 elements, or as we say, a subgroup of order 3. So in this case, something that wasn't obvious at first glance is that the cyclic subgroup generated by this particular matrix is nothing more than just a subgroup with 3 elements. The element itself, A, has order 3 in the group GL2Q because it generates a cyclic subgroup which has exactly 3 elements. So these are sort of, you know, 2 things that can happen when you look at the cyclic subgroup of an infinite group generated by some particular element. It can be itself an infinite group, or it can actually turn out to be finite. So that's kind of a slightly surprising example. You know, if you write down a random 2 by 2 matrix, this is unlikely to happen. Okay, that's the concept of a cyclic subgroup. And, I suppose there's quite a bit there in terms of both the concept and the notation that goes with it. So if you want to try out a few more examples like this in some groups that we know about, I think that would be definitely a good idea and something to practice with. Okay, that brings us essentially to the end of this bit and to the challenge for this week, which is kind of a theoretical point, and it's sort of a technical point as well, something to think about. So basically the question is, we're talking about subgroups here, and the assertion is that if you've got a group G with some operation star, then a subgroup of G is a subset of G, which is itself a group under the same operation star. So it includes some, but not all of the elements of G typically. And the question here is, it's kind of a slightly subtle one, which is it possible that you could have a group G with an operation star, and it could have a subgroup, but that the identity element in the subgroup could be a different element from the identity element in the whole group itself? So could there be some element which acts as the identity element on the subset H that's different from the element that acts as the identity element on the whole group? Okay, could that happen? So your challenge is to either give an example where that does happen, or to give an argument reasoning from the group axioms to explain why it never could happen. Okay, so it's another kind of challenge. So your task really here is to come up with an argument or a proof that this couldn't happen, or with an example where it does happen. Okay, so have a go at it and see you soon. That's it for this one. Next topic is generating sets, which is closely related to this concept of cyclic subgroups. Thank you very much, everyone.